Okay, so welcome back. So I added here a one word to the title of the slide and non-numelity. Okay, so we're going to look at not only heteroscedasticity but also non-numelity. And just like I alluded to before, we are assuming when we are estimating the Tobit model homoscedasticity, so the conditional variance of the error term conditional on x does not depend on x. And then we also assume that the errors were normally distributed. Okay, so in the linear regression model, it's not really a big deal to violate those assumptions if you have lots of independent data. Essentially, you can estimate the linear regression model without caring at all about how that is distributed. In some sense, OLS is a semi-parametric estimator in the sense that it's not making any parametric assumptions about what the distribution is of of um, of the random components. Okay, it only makes assumptions about the conditional mean of y given x. Okay, so then we are making more assumptions now in the context of the Tobit model. We are assuming that this error here is normally distributed. And it turns out that this assumption is something that we need to have, right? Because otherwise, how could you derive all those conditional means, right? Since that we looked at in the previous video, because they all depend on that normality assumption. So it was some other distribution. Well, you have to derive those conditional means again. Okay. So we are really so if we here suddenly assume heteroscedasticity, allowing this one to be, say, depend on x, right? It could be that you have this specification. Well, then it's a different model, and all those conditional expectations and likelihoods going to be looking different. Okay, but that's not what we did. So I want to analyze what is the effect of ignoring those specification assumptions and just still use the Tobit model. Is it still robust to those misspecifications? If you were doing a linear model, they would. Okay, that would be, you would get exactly the same estimator, because the maximum likelihood estimator for the linear model with epsilon being normally distributed is identical to the OLS estimator. Okay, where we're not assuming making any assumptions about the error term. Okay. So it turns out that basically the maximum likelihood estimator is really relying on that distribution. Essentially, the difference being that in the center part of the distribution, you don't know what's going on. So in order to make inference about how y is distributed, well, you need to say something about the distribution, the unobserved part of the distribution. If that is wrong, well, then your model is wrong and your parameter is going to be inconsistently estimated. That applies also to the case of consistency. It's essentially a misspecification of the distribution of the error term. Okay. So it turns out the Tobit model really heavily relies on normality and homoscedasticity in order to get consistency. What can we do? Well, we can estimate the model, extending the model and allow for some sort of specified correlation. Then, to the extent that that is flexible enough to capture the source of heteroscedasticity that we have in mind, well, you're going to be fine. Okay. If it's wrong, well, or not flexible enough, you're going to still be in trouble and get inconsistent estimates. Okay? And that's what you do with maximum likelihood. You need to fully specify the entire distribution in case you don't have observations for part of that distribution, and then those assumptions start to become very important. Okay, and the same argument goes for the distribution of the errors. Okay, so whatever you need to do, you need to I mean, it turns out these assumptions are actually quite important. Okay. So here, what I've done is I've essentially generated a bunch of different errors. Okay, some errors were normally distributed, and some errors were basically log normally distributed. Some errors were uniform. Some had a mixture of two normals, and some were where the distribution would be symmetric. And then another one would be an asymmetric distribution. We can look at all these, so we can try to see how robust are our estimates for the Tobit model, subject to all these different types of misspecifications. So I'm going to simulate data under different sampling schemes and then estimate the model with the Tobit model and see, can I estimate beta and sigma consistently, even though I misspecified my model in this particular way. And so I do that. So first, just for completeness, I plot the distribution of the histograms so you can see them. And then I run the Tobit model on these data where these areas have different distributions that are not normal. So the first one is going to be the normal distribution. Oh man, so what is not here? I added this. Okay, I don't know why I did this. Okay, we need to probably, zoom out a little bit and, go and work, go out of the rice mode. So the first case here, that's where we assume the error is normally distributed. And let's just memorize now, what are the parameters set to, okay? We're gonna memorize what that is, okay? The parameters beta is 0 and for the constant and 1 for the slope, and sigma is equal to 2, okay? 0, 1, 2, okay? That's easy to remember. And Tobit nails it, just like before, okay? When errors are generated from this distribution, and essentially does not depend on the explanatory variables, well, then you're gonna get nice results. Okay. Then let's move on to another distribution, say the log normal distribution. Okay, error is not normally distributed anymore. They have this distribution. They still have mean 0. They have the same variance. I normalized it so they have the same variance. I don't want to, impose that we suddenly have much more censoring in this particular case. So we have like 50% of the sample censored in the former case. We still have, well, it's a little bit more censoring, okay, but not much. What you see here is now the estimates really go berserk, right? I mean, you got in the censored part of the distribution, you got a whole different distribution than normal one. So you got a constant that's minus 1.5, that should be 1, or that should be 0, this should be 1, it's almost twice as large, and the standard deviation of the normal distribution is really totally out of the blue, should be 2, and then now it's 3. Okay, so misspecifying the distribution, if they're in fact skewed, or they had some skewed distribution, then you're going to get very funny estimates. Okay. Now you can say, well, maybe a log normal distribution of the error is not the best example, but it's too skewed. Can we estimate the model under somewhat milder assumptions? Okay, so here's some errors generating from a uniform. And you can see here, it's not as devastating for the parameters. They should be 0, 1, and 2 as in the previous case, but still, even with 5,000 observations, where we really nailed it, if we're having assumed the normal distribution, we're starting to see some deviations, and you can see they're actually significantly different from the true value if you were to trust these standard errors that are coming from this model that is inconsistently estimated. You can generate all other sorts of distributions, and actually I encourage you to go in and look at the code that's generating that error distribution. I have that here. It's called sim error. So you have all these different choices, and here's the one that we're looking at now. So that's a mix of 2 normals. And basically what I'm saying is, with probability 1 or 1.5, you're coming from one normal distribution with mean -2 and standard deviation of 1, and with probability 1.5, but that 1 minus that probability, you come from another distribution where the standard deviation is the same, but the mean is 2. Okay, so that's what you essentially see here. Okay, so you got this funny shaped distribution. It's like this 2-point distribution. Like you think about this like 2 types of people in the sample. You didn't account for that in your model, and you suddenly got this mixture of 2 normals. Okay, so because of, say, unobserved types, and so we still have this, roughly around half of the data is censored. I got same mean and standard deviation because I normalized everything, and let's look at the results. Okay, you got a little bit of deviation here from the true value. But it's not as bad as a log normal. And turns out what really makes a difference here is the skewness of that distribution. And you look at this this metric, this mixture of two normals that have essentially different variances, and suddenly you get this funny shape. Now you start to see more deviation. And of course, if you start to have more variance of the error term, so of course that misspecification means more, right? You can still, in this case, for the logit with normal errors, they're still within the confidence intervals, but then you move down here and you start to see some funny things going on, right? Um, so what the bottom line here is really, let me put the right back. The bottom line here is, if you're not making, if you're not satisfying these assumptions, you're going to make a big, you're going to make a big, you're going to potentially make some mistakes, right? And those mistakes, well, they depend on the shape of those distribution, but they also depend on how much censoring you have. So if I say increase this with, say, the constant to 10, so there'll be no censoring, it doesn't really matter what the distribution you were choosing, right? You're just doing linear regression. You got coefficients that are 10, 1, 1, 1, 2, 10, 1, 2, 10, 1, 2, 10, 1, 2 for all these different distributions. Okay, it doesn't matter what the distribution is, because the maximum likelihood estimator is collapsed to the like to the OLS estimator, because that part of the likelihood that has to do with the censoring part is now gone, and you're left with a part that is for the continuous part of the distribution, which is, so you end up with a likelihood function that's identical to the likelihood function for the linear model with normal errors. Okay, we know from econometric Z that the maximum likelihood estimator of that model is equal to the OLS estimator. And you can estimate OLS solely from moment restrictions on assuming that conditional mean of y given x is equal to x beta, not even making any assumptions about what the distribution is. And this is an illustration of it. Okay, so unlike the case where you have censoring, we don't have any problems with normal distribution, with non-normality or heteroscedasticity for consistency of the estimator for the linear model. Only in the case of censoring and corner solution outcome model. Anyway, let's go back to the slide deck, see if I can make some concluding remarks. So basically, the Tobit model offers an appropriate specification for censored variables and corner solution outcome models, but it relies really strongly on the distributional assumptions for consistency of the maximum likelihood estimator. So you can't have non-normality, you can't have heteroscedasticity. I didn't show that, but that's the same thing. And then, but then fortunately we can actually estimate the model under weaker assumptions. That's something called the centered least absolute deviation that is described in Woolrich. I may talk about that later. And that's a semi-parametric approach where we're not making any assumptions about the error term. Okay, that makes that estimator more robust, but then it turns out you can identify less, right? Because if you were to identify beta, would that be enough for you? Well, you still need to get all those conditional means and probabilities. These are objects of interest, and you can't get those without making any distributions, distributional assumptions for the unobserved part of the distribution. Otherwise, you can't. I mean, a conditional mean is derived basically by integrating over the distribution, right? So you need to know what that distribution is to get those means. Okay, and here you can make all sorts of other extensions. For example, you can have like double centering, where there would be centering in several parts of the distribution, or you can have interval regression, where there'll be several intervals that will be collected in mass points, and then derive, basically, you can derive the likelihood from this choice rule instead. That's actually a good exercise. Sit down with pencil and paper and you can work it out. So anyway, I think we'll stop for now, and see you soon.